Okay, so it's 10 a.m. If you want, Rachel, if you are ready, we can start.
Okay, sounds good. All right, hello everyone. I'm very pleased to be here leading you through some tutorial problems related to what you covered in lecture this week. And hopefully being able to work through some problems will give you a bit more practical understanding of what you've already seen. And so I think my recommendation for this is to get a pen or a pencil and some paper, because while I'm going to try to keep my screen showing things as much as possible, it's not always going to be possible to show you the problem statement along with the answers at like a size that's readable. So I recommend like writing down a few things about the question so that when I'm going through the answer, you remember it, because you won't always be able to see it on the screen. All right, Veronica was kind enough to provide me with some problems that are related to the lectures, and the first one is a group theory problem. So we're going to start with question 1A, and I'm not going to do all the questions in order because I'm not sure we have the time to do everything, though if we have extra time at the end, I may go back to questions we skipped. But the first one we're going to do is 1A. So problem 1 says that you consider a vector Q that transforms as if it's in the fundamental representation of SUNC. And then she reminds you what that transformation looks like. Q goes to Q prime, where Q prime is the result of operating a U matrix on the original Q, where U is defined as the exponential of minus I times a parameter times a generator. And as is typical of SUN, there are n squared minus 1 generators. And then she also defines, and then the problem also defines a vector Q dagger that transforms according to the conjugate representation. And the first question is show that the generators of the conjugate representation, which are given by T bar A, are the minus of the generators of the fundamental representations raised to the transpose. All right, so I'm going to make this window a little bit smaller, but you can still see the question for now. And then I'm going to move over to the handwritten answers, where I've also written out the question again, but eventually I'll have to scroll away from it. So now I'm going to switch to this window, and you can see I've written the question again, so you can still see what the question's asking while I go through the answer. All right. Sorry, let me just moving my Zoom screens around so that I can see the window. Okay, great. So, do that one more time. So here's again the question written out. All right, so I'm going to introduce some notation that's really common in particle physics, where the fundamental representation is shown as a box. So often we'll say that this box is the fundamental representation, and then we also often call the conjugate representation as a box bar. And I apologize, my handwriting in this live screen is going to be a little bit more messy than what I wrote out beforehand, so hopefully you can follow what's going on by reading what I've already written out. And so, all right, so what do we do to prove how the conjugate, the generators of the conjugate representation relate to the generators of the fundamental representation? So the first thing we do, and now I am going to scroll away from the question, so hopefully you've had enough time to write it down. So the first thing we're going to do is we're going to say, okay, so the conjugate is, when under the transformation, you multiply it by some matrix, right? Some transformation matrix, which we're going to call U bar, but we haven't specified what U bar looks like. And then in indices, what this looks like is that, you know, like when you take a Hermitian conjugate of a vector, if it starts as a column vector, you get a row vector, but the elements are complex conjugated. So I'm going to write this in terms of the elements of the vector. So you can see Q star I. And then that goes to U bar ij, which are again some unspecified elements of this conjugate transformation matrix times Q star j. All right, so now this is, I haven't really used any information I know, I've just sort of rewritten things. But now we are going to use information we know, which is that Q is the Hermitian conjugate, Q dagger is the Hermitian conjugate of Q, right? So that means the Q dagger prime is the Hermitian conjugate of Q prime. So we can write Q prime inside of this Hermitian conjugate, and then we can perform the operation. So you get Q dagger, U dagger, And then you can rewrite this out in terms of the elements, right? So this Q dagger is again Q star I. And this now gets turned into Q star J times the elements of U dagger, given this multiplication rule. And then you know that like the dagger is really the complex transpose. So you can rewrite U dagger Ji as U star Ij. And you find that Q dagger transforms also like this, where now U tells you something about the fundamental representation. So you can set these two things equal. So you can say that this and this are equal, right? And so now we can say what U bar is, like what the matrix elements are. And so we can say that U bar Ij is U star Ij, which isn't very surprising because the name was conjugate representation and it's the complex conjugate. So the naming convention makes sense. And so now we want to know, like, now that we know how the matrices, the unitary matrices are related, how are the generators related, right? And so this is just some simple algebra to write it out. But I'm going to go through it slowly just so you like have this in your mind of what like all this terminology means when you sort of unfold it and look at the underlying elements and matrices. So rewriting U star again, you know that U star is U dagger transpose, right? Because the dagger is the complex conjugate transposed, and then two transposes gives you the original. And then we also know that U is a unitary matrix, right? So U dagger is the identity matrix, meaning that U dagger is U inverse. So we can write this, and then we know what the inverse matrix is. So if the original matrix, U equals e to the minus I theta A Ta, we can write the inverse as the plus of this, and then we get where these are the original fundamental generators, and we can find that U star equals this. And then we also know that just based on like the definition of U is e to the minus Ia times the generator, that the conjugate unitary matrix is related to the conjugate generators this way, and we get this. Let me circle that more clearly so that it's not covering anything. And then these two we can set equal, and we find the relationship that we were looking for. So there wasn't anything, which is that the conjugate generators are just the negative of the transpose of the fundamental generators. So that's how the generators, oops, sorry, 1 second. I didn't mean to scroll you away. Okay, so this is how the generators of the conjugate representation are related to the generators of the fundamental representation, where I'm still trying to kind of get you used to this box bar notation because you'll see it a lot in the literature. So basically this is just like some really, really simple algebra. So I don't think this problem is meant to like show you how to do matrix multiplication, but I think the idea is just to get you used to like the kinds of manipulations that you use so that you can see how things are related to one another, and like that what this terminology, which can sound kind of foreign, like really means when you unpack it. All right, so now I'm going to move on to the next question, unless there are any questions about how I went through the solution.
I cannot see any question right now.
Okay, great. Okay, so let's look at the next question. So I'm going to navigate away from this window, and then go back to the nice teched up version of the question rather than the handwritten version. So sorry, it's just there's like Zoom panels in front that make it hard to navigate. Okay, so I'm going to actually skip the next two for now. I think they're really interesting, but for now I'm going to skip them, and maybe if we have time we'll go through to the end. But I want to make sure we cover everything. So now I'm going to go to question 2. And question 2 says, okay, now moving away from just the fundamental representation, let's say we have some general representation R of a compact Lie group G. And we want to consider something called the quadratic Casimir operator. And all the quadratic Casimir operator is they call it T squared of R. which is just multiplying two generator matrices, but they have the same group index. So it's TA of R times TA of R. And part A says, show that T squared commutes with every generator of TA. And if that's true, the nice thing we can do is we can write T squared of R as just a number times an identity matrix, where the identity matrix is the right size that it can multiply matrices in whatever this representation is. So in the representation, you know that you'll have these generators will look like matrices, and they'll be like some size, let's say n sub R times n sub R. And so this identity matrix is like n sub R size so that it can multiply these matrices. Or another way to say that is that it's living in the vector space spanning the representation R. Let's go through this question. So I'm going to navigate away from this window, but I did rewrite the question in my handwriting. So you'll get another opportunity to copy it down if you haven't finished writing it yet. So moving here. Okay. Okay, so I've rewritten the question here, and I'll try to keep it on in the window as long as possible. All right, so we want to show that T squared commutes with any general generator in this representation of the group. All right, so another way to say that is we want to show that T squared, where this is the quadratic, apologies for the handwriting, Casimir. Although Adobe is kind of making it neater for me, which is nice. Still not very neat. But this is the quadratic Casimir, and this generator on this side is just any generator in the group. Just gonna say just any generator. Okay. Writing out the quadratic Casimir, and now I'm going to change indices. So I'm going to call it TB times TB. You know that this is an internal index that's summed over, so I can call it whatever I want. So this is the commutation relation I want to show as 0. And so then you can use properties of commutation relations to rewrite this like this. And then you know that these commutators, this guy and this guy, form structure constants. And so you can write them out as FBAC times TC, so structure constants times another generator, where maybe I've missed some prefactors, but we're showing this equals 0, so those aren't very important, unless there was some cancellation, which doesn't occur here. All right, so already in this line, you can see that this expression should be 0, right? Because it's anti-symmetric in B and C, because these structure constants are anti-symmetric, but it's symmetric in, okay. So it's both symmetric and anti-symmetric in B and C, although now that I'm looking at it, it doesn't quite look that way. But let's just reindex it to really check that that's true. So 1 second. Yeah, so if you really check that this is true, you can reindex. So you can rewrite this, and then you can reindex, and you get that these two guys cancel, and you get 0. So moving on. Oh no, sorry, this is definitely symmetric in B and C because these two terms are symmetric. Okay. So that's kind of nice. And so because of this commutation relation, you can see that you can use this nice relationship that the quadratic Casimir is just a constant times the identity matrix. And so now we can do more things with that. So I'm going to move back over to the question statement to show you part B, tucked up nicely. Okay, given that the generators of each representation are normalized as follows. So if you take the trace of one generator and another generator, TA and TB, you have this number TR times delta AB, where TR depends on the representation. They ask you to prove this relationship that the quadratic Casimir of a representation times the dimension of the representation is this TR, which is actually called the index of the representation. So I might call it the index, but I'll try to maintain the note. I'll try not to throw too much terminology at you and just call it TR. But if I slip up and say index, TR is the index of the representation times the dimension of the group. So moving back over to the solutions. If you haven't had time to write it down, it's handwritten over here. Okay, and I'll try to keep it on the window as long as possible. So they want you to show this relationship. And I'm actually going to introduce something called a bird track diagram, which I think is kind of a nice way to sort of like really quickly get a visual intuition for group theory. And a bird track diagram is like inspired by Feynman diagrams, but they're not actually Feynman diagrams. Although sometimes like you can use a lot of the intuition from Feynman diagrams in bird track diagrams. And so the way bird track diagrams work is they say that this generator TAIJ can be represented like a vertex A times I and J, where I and J are representation dependent, but A is always it's like the group index. So you can think of it as like a particle in the adjoint representation, for example. That's why it has a wiggly line, like a gauge boson. And so, for example, like if you do have a Feynman diagram, that's like a gauge boson, say interacting with, I don't know, like a quark, say this is a gluon, then in fact, in that Feynman diagram, there is actually like a factor Tij, where this is the fundamental representation. So like the group theory of the Feynman diagram will reduce to this bird track notation, like in some examples. So the intuition can be quite useful. But I and J are representation dependent. So this correspondence is most useful if you're in the fundamental representation, because most particles are in the fundamental representation. So that's when this is going to be really useful. But here we can use this diagrammatic notation to actually immediately show that this relationship is true. And so like, if you want to do these diagrams, you can write out a diagram that is the quadratic Casimir operator, right? So the quadratic Casimir is two of these guys multiplied together, but they have the same A and the same J because the matrices are multiplied together, right? So if you write, okay, I have Tij, Tajk, and then I connect A and J. So I connect these lines. And then I write it neatly, right? Because you can always sort of deform Feynman diagrams into a nice way. And so then the quadratic Casimir operator is just this diagram, right? So I've written that here. So that's really not, that's like a nice way to look at that. And then you can do the same for the index of the representation, right? So the index is the trace of TA and TB. So now A and B are different, but this trace means that like the indices are related, right? So I can write out this trace in index notation like this, and then I can write my two generators, but now J is connected by the matrix multiplication, and I is connected by the trace. And so you get a diagram, so you can write it like this, but then you can write it more neatly and you get a diagram that looks like this. So this is a diagram that's the index of the representation, or this is a diagram that's TR. And so if you want to show that this relationship is true, you can immediately show this. So we have CR and TR, and we can immediately show this relationship by closing this and closing this and realizing that these guys are the same diagram. So I've written that more neatly below here, right? And if you don't see that these are the same diagrams, maybe another way to do it is to deform it sort of equally. So I do a quark loop here, or sorry, a fundamental loop here, and then an adjoint here. And you can see that this diagram, if you sort of like zoom in on this and sort of like shrink this, you get this diagram. But if you instead shrink the fundamental loop and you increase the gauge boson loop, you get this diagram. So these are the same diagram, and then you can just calculate them. So in this diagram, you can see that here, this little tiny piece is the quadratic Casimir, right? And then this is, you have to sum over this extra loop you added, which is a sum over I, right? And then I goes from like 1 to the dimension of the representation. So in the fundamental representation, if this was a quark loop, there would be n quarks running in the loop. But in this representation, there's I goes from like 1 to the dimension of R, so whatever the size of the matrix is. And so you get this relationship. And then if you look at the same diagram a different way, this little guy is TR. And then here we sum over what's left over in the loop, which is all the gauge bosons in the loop. Like they're not actually gauge bosons, but like analogously gauge bosons. And so this sum is how many gauge bosons, which are always n squared minus 1, because the adjoint representation always has n squared minus 1. Or another way to say that is the dimension of the group is n squared minus 1. So this is the dimension of the group, right? And so in this way of looking at the diagram, you get this result for the diagram in terms of like the group theory structure, or like the group theory multiplicity if you want. And so because those two diagrams are the same, you can show that the dimension of the representation times the quadratic Casimir is the dimension of the group times TR. And so this might seem more time consuming than proving it with indices, but I think that's because I had to explain what these diagrams are, but I think they can give you some really quick like intuition for what group theory is going on as it gets more complicated without having to like dig through and like do like index manipulation. But of course you always can dig through and do index manipulation. And so in the second part of this, I did that in a few lines. Here, maybe I'll try to show as much on the screen as possible. And it's not so possible. Okay. So to do it with indices, the quadratic Casimir operator, when you write it out in indices, is this. And the TR, the operator that corresponds to this trace, when you write it out in indices, is this. And you can see they're really similar, right? This guy has A and A equal. This guy has I and I equal instead of IK and AB. But if you wanted to make these two the same, in the top line, you set I equal to K. In the bottom line, you set A equal to B. And then these two expressions, these two numbers are the same, which corresponds to CR times delta II, and you're summing over I. So that gives you CR times the dimension of the representation, and this gives you TR times delta AA, so you're summing over A, where A is like this, A is the group index. And so this gives you TR times the dimension of the group. And so because these two numbers are equal, you can again show that this relationship is true. So yeah, any questions on this problem before I move on to the next one?
Yes, Richard. Actually, after a little bit that you started this problem, there have been 3 questions. So probably they refer to the previous problem, but okay. We'll let you know that. So the first one is regarding to the fact that if you can send me the PDFs of the problems, I can upload them in the school page, so they can have access to the text of the problems. But this you can do later, and we'll upload it later. So why do we get a result T squared equal to CR identity? So it's the previous problems.
Yes. So this follows directly from the fact that T squared commutes with every generator in TA, right? So that means like the only object that commutes with every generator in TA is something that's proportional to the identity, right? So that means we know that C squared is some number times something proportional to the identity.
Yeah. So to the question, once you prove that they commute, then you prove directly that T squared is proportional to the identity.
Exactly. Yeah. Yeah. So I guess it depends on how you want to read the question. I was reading it as show that this commutes with every generator, and then a fun fact is that this is implied. But if you want one extra sentence, then proves both are true at the same time.
No, it's fine. And the last question: the structure constants are always fully antisymmetric for any compact Lie group?
Yes. I think that's true. Yes.
Okay, very good.
Although I will admit that I work with SUN and like SON more than any of the others. So if a counter example exists out there, it's very uncommonly used. But
correct. I do agree with you. No more questions for the moment.
Okay, great. Yeah, thank you.
Thanks to
okay.
you.
So let's move on to the next question. Okay, so we spent about half of the class on group theory. So now I want to move on to some quantum field theory and hopefully do some fun symmetry breaking stuff. But the group theory is really important. So if we have time at the end, I'd love to go back and do more of these questions because it's like, I think it's kind of the skill that's so useful in day to day, but it's not always covered in lectures. Okay, so let's skip past this question and move on to, let's see, do we have time? I'm going to try to do problem 3. All right, so problem 3 introduces a Lagrangian. And the Lagrangian describes 2 Dirac spinor fields. So there's 2 kinetic terms here in the first 2 terms, and then a mass term here in the last set of terms. And they tell you the definition for a conjugate Dirac spinor, which is psi bar is psi dagger times gamma naught, where gamma naught is one of the gamma matrices, one of the Dirac matrices, and M is a real parameter. And so I'm sure you've seen Lagrangians like this in the past, but I am trying to read slowly so you have time to write things down. All right, so we've seen in the lectures that this Lagrangian is invariant under a global U1 cross SU2 transformation that looks like this, where psi goes to e to the minus alpha, so that's the U1 transformation, and then in addition, it also transforms like Uij psi j, which is the SU2 transformation. And then the Uij is described by an exponential of minus I times some parameter alpha, and then a Pauli matrix, sigma A divided by 2. And it's actually a sum over all the Pauli matrices. And so you see that alpha, alpha 1, alpha 2, alpha 3 are real parameters that are constant, and then the sigma A are the Pauli matrices. And so for part A, it's going to say, okay, so we know that this Lagrangian is invariant under a global transformation, but now consider a local transformation, where it's exactly the same transformation as in the introductory description of the problem, except now we're going to say that these parameters that were constants before are now dependent on spacetime. So alpha becomes alpha of x, and then very generally the matrix UI is UI of x. But specifically inside this matrix, these parameters before that were these real parameters that were like coefficients of the Pauli matrices are now functions of spacetime. So alpha x, alpha and alpha a of x are all arbitrary functions of the spacetime point x. G1 and G2 are just are now arbitrary constants that don't depend on x. And it wants you, or the question asks, to show that the Lagrangian is not any more invariant under this transformation. And if it's not invariant, what is the variation of the Lagrangian? All right, so if you didn't have time to write it down while I read it, I'm going to move over to the problem statement where I've handwritten it. So problem 3 here. Okay. All right, so what we want to do is we want to show that this Lagrangian is no longer invariant under this new version of the transformation. And we have here the Lagrangian, where now I've written it more simply. So I've written, instead of like individually psi 1 and psi 2, I've written in terms of the field psi, which is so that things like psi bar psi are like, you can think of them as, and so you get these terms come out, right, that are just summed up. So I've tried to condense the notation of it into just these size fields. And so now let's do the transformation. Sorry, I'm scrolling away from the question. All right, so the first thing we do is we operate this transformation on the psi living inside psi bar. So as you know, psi bar, it's written in the question, is psi dagger gamma naught. And so what you have to do is you write, let's see, 1 second. So yeah, so what you do is you you do this transformation on psi dagger, And then you try to commute things past each other to rewrite psi bar. And so we get this here, and then we get this here. And since there's no gamma matrices in here, you don't have to worry, like the gamma mu is living on this side of secretly gamma naught. So you can move gamma naught back here and put it back inside the psi bar. And so we get this partial derivative here in the kinetic term. And then we also do the mass term. And the mass term is still invariant because the mass term didn't care whether this was a global or a local transformation. In the mass term, the U1 transformation cancels just because these arguments of the exponents like add up to 0. And then similarly, the SU2 cancels because U dagger U equals 1. So the mass term is invariant, which you see in the next line here. So that's good. But when you take the partial derivative specifically on this term, you're going to get extra terms because the partial derivative is going to pick up things from these local, from these space-time dependent parameters in the local transformation. And so I've written that out here. So you take the partial derivative and you hit and you grab things like partial mu alpha from the U1 transformation, partial mu of the unitary transformation associated with SU2, and then this guy, which looks like what you got in the global transformation. So this guy probably won't contribute to delta L. And explicitly we find that. So I try to condense things out and I pull out factors that do in fact cancel. And we end up with these leftover pieces again. And so rewriting it, we find this guy, this term, does in fact come back into the expression that looks like the original Lagrangian. The mass term also does. But these extra terms here show up in the variation Lagrangian. So that if you say that L goes to L, sorry, 1 second. This happens sometimes with the pen. I'm not super great at using it yet. All right, so L goes to L plus delta L. Oh no, again. Plus delta L. Then you find that the delta L terms are these extra terms left over. And so you can say that the variation of the Lagrangian looks like this. And so here we can clearly see that a local transformation, just because the global transformation left the Lagrangian invariant, the local transformation might not. And specifically the problem comes from the kinetic terms because of the kinetic terms involve partial derivatives that then pick up pieces of these functions. So let's go to part B of this question, which is where we do something a bit more interesting. So in part B, it says, we can modify the Lagrangian actually so that it is invariant under local transformations. And that means promoting the partial derivative to a covariant derivative. And this is probably something you've seen before, but if not, this is a pretty important concept in quantum field theory. And so we define this new covariant derivative as the partial derivative plus factors of these new fields, B mu and W mu, which are the gauge boson fields associated with the electroweak gauge group in the end. And they are modified by these G1 and G2 couplings. And what the question asks is, all right, B mu and W mu are new fields. How do these fields transform to ensure that L is now invariant under the local transformations, to make sure this covariant derivative does what we want and keeps the Lagrangian invariant under local transformations in addition to global transformations. So moving back to the question, where I've written this out again. So again, we see here I've rewritten the covariant derivative. All right, so what do we do? So already we know how L transforms because we found it in the last section in terms of these other, in terms of L and delta L. But now let's rewrite it in terms of B mu and W mu. So we're going to say the transformation here proceeds as it did last time. And the transformation here now involves a B mu prime and a W mu prime, where for now we don't know what W mu prime and B mu prime are. And then we keep the other constant factors. And we know that the mass term is invariant. It still should be invariant as it was last time because there's no partial derivatives involved. And then if we write this out, we get these transformations. So we now have to operate this partial derivative on these guys again, which we already did last time, so we know the form of this. So we get these three terms, which we're familiar with from the last part of the question. And then we also have these extra terms, b prime and w prime. And so we can gather everything together in terms of delta L, where this is like the answer to part A, and these are the new terms. And if we want delta L to vanish, we can set b mu equal to this part. So if these prefactors will cancel because they're equal and opposite, and the whole terms will cancel as long as b mu prime transforms like this. And then for w, we need the w mu prime to transform like this. But this here for the b mu, we're done. We know how it transforms. For the w, we sort of have to, the w mu prime has this like sigma a next to it. So we want to isolate w mu prime. We don't want to just know how w mu prime times sigma a transforms. But that's pretty simple. It's just a bit of algebra. So we say, all right, we know w mu prime times sigma a gives you w mu a times u dagger sigma a u plus this other piece, mu dagger partial mu u. And then one way to like isolate w is to multiply both sides by sigma b, right? Because then on this side, you'll get this nice delta function. And so you'll get w living alone. And so then we multiply through by sigma b on both sides here. And then this, when you apply the delta function, w mu prime a becomes w mu prime b. And then you get this relationship where w transforms like w plus these times this plus this extra piece here. And then we already knew how b mu transformed. So yeah, so now we can see that like with transforming gauge fields, we can restore local invariance over, and so we can take a Lagrangian that was globally invariant and make it locally invariant. So are there any questions about this part?
Seems not yet.
Okay, great. Yeah, this is maybe this is a bit boring for you guys and you want to get into like some lecture week symmetry breaking. So let's move on to those questions now that we've sort of done the basics of like how these group theory things work out. All right, so on to lecture week symmetry breaking. All right, so we have 20 minutes left. So let's start with the easy question and then we'll do the hard question if we have time. All right, so it starts with question 1. Consider the following Lagrangian for a real scalar field in a Dirac spinner. And so this Lagrangian is, again, probably similar to something you've seen before. We start with a kinetic term for the scalar field minus a scalar potential. And then we have a kinetic term for the Dirac spinner, and then a term that's a coupling of the scalar to the Dirac spinner, so Yukawa coupling. And then we specify the scalar potential this way. And then, you know, of course, lambda needs to be greater than 0. So this is a potential that's bounded below. And so the first thing it says is show that this Lagrangian is invariant under this transformation. I'm actually going to skip it because we've done a lot of group theory. So let's move on to symmetry breaking. So the next question, sorry, let's see if I can get everything on the screen at the same time here. The next question is says that, okay, as you know, ground state configurations for scalar fields are those that minimize energy. So if you minimize energy, like that means that there's no kinetic energy and you're sitting at the minimum of the potential. So you're not like, you know, a very, very vague analogy with classical mechanics is like, you're not like a ball that's like oscillating about the minimum, you're just sitting at the minimum. So no kinetic energy and you're at the point of an extreme minimum of the potential that corresponds to a minimum. So it says find the ground state configuration of this, this field phi in the case that this prefactor inside the potential, mu squared, is greater than 0. And what particles, spin, and masses does the Lagrangian describe? So that's the first part. And then in the second part of the question, it says, all right, now consider the case where mu squared is less than 0. Show that the ground state configurations have this other, obey these other conditions. One is that the ground state is no longer such that phi is 0, but instead phi is plus or minus v, and v is minus mu squared, not m squared. Sorry, there's a bit of a typo here, over lambda. And then once we have that new minimum, the question asks that you expand the scalar field around the minimum in terms of this new scalar field h. So phi is the minimum vacuum energy plus h, the vacuum excitation value plus h. And then it wants you to rewrite the Lagrangian in terms of h, and then find the particles that the theory describes in this case. All right, so let's do that. I'm going to move over here to the answers for part B. And I'll try to keep the question up on the screen as long as I can. Okay, so case 1 is quite easy. So the first one is to minimize the potential for mu greater than or equal to 0. All right, and so what you can do is you just take the first derivative of the potential with respect to phi, and you get this expression here. You can factor out the phi, and you find that there are two values of the field that can give you this extrema. One is that phi naught is equal to 0, and the other is that, sorry. Okay, and the other is that phi naught is the square root of negative mu squared over lambda. And so this guy looks like pretty bad for the case that mu squared is greater than 0, because this is the square root of a negative number. So we know phi is a real scalar field, so this isn't really a valid solution. And so the minimum really exists at phi naught equals 0. And if that's the case, then this Lagrangian is describing the physical particles that are present in the theory, right? So the two physical particles are phi and psi. Phi has spin 0 and mass squared equal to mu squared, and psi is a fermion, Dirac fermion with spin 1/2, but its mass is 0 because the Lagrangian didn't have a mass term for this fermion. So this is a massless Dirac fermion. All right, so now let's do the interesting case where mu squared is less than 0. So in this case, we still have, like, the algebra still shakes out, right? So we still have the same two minima, but now mu squared is negative, so minus mu squared is positive. And so this is now another valid minimum. So there's 3 possible minima, right? 0 and then plus or minus v. And now v is in R. And I've chosen, like, the minima can be plus or minus v, but I've chosen v to be a parameter that's positive. All right, so of these 3 minimum, which is like the true minimum, which is the lowest of these 3 local minima. And so one way to do that is to just plug this v back into the potential and see what you get. So we know that, so the potential is 1/2 mu squared phi squared plus 1/4 lambda phi to the 4th. So if phi is 0, then in the first minimum, this just gives you 0. So if we plug v in and we get something less than 0, then we know that this is the real, this guy would be the real minimum. So let's see what we get. Plugging v in, we get 1/2 mu squared v squared plus 1/4 lambda v to the 4th. And then factoring things out, you can rewrite the potential like this. And then what you can do is you can plug in, because you know that v is the square root of negative mu squared over lambda. So v squared is negative mu squared over lambda. So you can plug that back in. And then it's multiplied by lambda, so the lambdas cancel, and you get this. And you find that the potential at that energy is 1/4 mu squared v squared. And you know mu squared is, we know v is positive and real. So v squared is definitely positive. And we know mu squared is negative because that's what we assumed at the beginning. So this energy is negative. So we know that this is the true, this is lower than 0, and this is the true minimum. And so that means that the minimum corresponds to phi is plus or minus v, and then already we showed from minimizing that v is the square root of minus mu squared over lambda, which is what the question asks. And so now the next part of the question says, well, what are the physical fields, right? So we have to expand. So we want to expand the Lagrangian. Phi of x is h of x plus v, where this is now a new scalar field. A new field. And we find, and I've rewritten the Lagrangian and the potential for you. So first expanding the kinetic term, we get the same kinetic term for h as we did for phi because the partial derivative kills this constant v. When we expand, so that's the kinetic term. The Yukawa term gives you two terms. So we get one term that looks like before we had the scalar field phi interacting with its fermions. Now we have this new scalar field h interacting with the fermions. But we also get this new term, which where phi is replaced by a constant value. And instead, we get something that looks like a mass terms for the fermions. So here we can see that the symmetry breaking gave a mass term to psi. And then the next step, so that's the Yukawa coupling. And then the next step, which is a bit of algebra, is expanding the potential in terms of h plus v. And so, you plug in h plus v for phi everywhere, and you do a bit of algebra. And the one thing I'll note is that whenever you get a term that goes like, say, lambda over 4 v to the 4, where there's no fields, it just depends on v, that's just a constant. And you can always like add some constant energy to your potential as long as it's finite. And so you don't need to keep track of these factors. You can always just subtract them away. But you do want to keep track of things that, that give you field couplings. And so we get something that goes like an h to the 4th coupling. We also get an h cubed coupling times a v. So it has like a dimensional coupling constant. And then we get a term that looks like a mass squared for h, which is this. And then if you simplify, again, using the same trick where we plug in the expression for v in terms of mu and lambda, you find that the prefactor for h is actually minus mu squared. And then we also get this linear term, but very nicely, the prefactor in front of the linear term cancels, so we don't need to worry about the linear term. And so simplifying this all out, we get that the potential for h looks like this. Plugging in the potential, we get the full Lagrangian, which is the kinetic term for h, kinetic term for phi's, which, sorry, I don't know if I've introduced this notation, but I'm using this notation where gamma mu, partial mu, is gamma slash. So that just means a gamma matrix contracted with a partial derivative. So that's what this is. And then we get, oops, this should be squared, mu squared, h squared, these other field couplings. So we have a mass term for h here, a mass term for the Dirac fermion here, and then the Yukawa coupling. And so the particles we have are h, which has a mass -2, the mass squared is -2 mu squared, but that's makes sense because mu squared is a negative number. And then we also have a massive Dirac fermion with mass g times v. All right, so I think, yeah, so any questions for this problem?
Nope.
Okay, let's see if we, let's see if we have time to do the last one where we actually get something a bit more interesting. The next one is we do exactly the same exercise, except for a complex scalar field. And oh, sorry, actually, Luca, I have one question. Can I go up until exactly 10 a.m. or should I let them go early to switch over to the CERN tour?
No, you have time up to 10 a.m. Then
okay,
I will provide a link and they will start immediately. So don't worry.
Okay, great. All right, so we still have a bit of time. Let's do this in a case that's more interesting. So we're going to look at a Lagrangian that's very similar, but has more degrees of freedom. So we have a scalar field that's not real. Now it's a complex scalar field. So you'll see a kinetic term has phi star times phi, and the potential depends on phi star and phi. And then we have a Dirac field that has that is written in terms of left-handed and right-handed components. So we have a chiral theory. And so so we see, again, a kinetic term for the Dirac field, but the Yukawa coupling now couples left to right, plus the Hermitian conjugate. And these left-handed and right-handed fields are defined by these projection operators. For the left-handed field, it's 1/2, 1 minus gamma 5 psi. And for the right-handed, it's the same except 1 plus gamma 5. And the potential looks quite the same as before, except because it's a complex field, you'll see different prefactors, but you'll see mu squared phi star phi, and then 1/2 lambda phi star phi squared. But this looks like a mass term, and this looks like a quartic interaction. And so we also know that the above Lagrangian is invariant under the global chiral transformation, where the right-handed fields go to e to the I alpha times the original right-handed field, but the left transforms like e to the minus I alpha, and then the scalar field transforms like e to the positive 2 I alpha. And basically, apologies, I'm going to scroll down, but I'll try to return if you need to write things down. So the question is basically, you can see here, asking the same questions as before. Consider the case where mu squared is greater than 0, and then find the ground state and the particles of the theory. Consider the case where mu squared is less than 0, find the ground state, and then find the particles of the theory, where they give you a hint as to how to write out or how to expand phi in terms of v, when phi is a complex scalar field. So what they want you to do is they write phi as a real component, and then imagine an I times a different real component. So you write it as sort of 2 real fields instead of 1 total complex field. All right, so now I'm going to move over to the answers, but I will, as I progress through the question, I will try to continue to show the pertinent information to answer the question as much as I can. So I've rewritten problem 5 here. Okay, so the first one, show that for mu squared greater than or equal to 0, we get this trivial minimum. And this is basically, I'm going to go through this really quickly because there's not that much that's different than what we did before. So it's not so interesting. But basically, the only difference is instead of you minimize, you just pick one field. So you can minimize with respect to the complex field or the complex conjugate phi star. And you get this expression that depends on phi. You would get a very similar expression if you chose to differentiate with respect to phi, which would just be the complex conjugate of this whole thing. And you get like a redundant answer. But in the end, you find a minimum of phi equals 0 and a minimum mu squared plus lambda times the modulus of phi squared, because now this thing that's left over is the modulus. And you'll see that lambda modulus phi squared equals minus mu squared. So this is a negative number in this case. We know lambda has to be positive to ensure we don't get infinite negative energy in the potential. And then we know like this modulus is a real number. And so the modulus squared has to be positive. So this is just like not a valid minimum in this case. So the physical modes in the case where the vacuum excitation value is 0 are precisely the physical modes of the original Lagrangian. So they're a complex scalar field of spin 0 with mass mu squared, and a Dirac field that's a fermionic field that's massless. So now we can do the interesting case, which is when mu squared is less than 0. So again, the two extrema are what we found before. One is 0, and one is that the modulus squared is negative mu squared over lambda. But now, because mu squared is negative, this is a positive number, so this is a valid minimum. And plugging it into the original potential here and here, we find that the whole potential is less than 0. Which is the case because even though mu squared is less than 0, mu to the 4th is still a positive number. So minus mu to the 4th over 2 lambda is negative. So this is now the true minimum. So phi naught 2 is the true minimum. And then we know, so it wants you to talk about what field configurations give you the ground state. And so there's some freedom here, right? Because all we know is that phi naught squared is some number, which I'm going to call, it's some number, right? Some real number. But that doesn't tell you everything about phi, right? Because phi is a complex field. When you take the modulus, you lose some information. So if we write phi as, like we can write any complex number in polar coordinates, if you like, as v, sorry. Let me go back. Okay, in polar coordinates, we can write phi as v times e to the I alpha naught, where alpha naught is real and v is real. Then you know that any alpha naught will satisfy this condition that the modulus equals some real number, which I'm going to call v squared. And so if you plot this in terms of like a plane of possible values of the complex field phi, you can, where like one axis is the real part and one axis is the imaginary, any value of phi that lives on this circle will satisfy this condition and will give you a minimum. So you have this continuous set of equivalent minimum, which you know from lectures should yield a massless particle based on the Goldstone theorem. So let's see if we get this. So the next part of the question says, what part, like expand phi in terms of fluctuations about its minimum, and what are the field configurations that you end up with? So that's part C. Or what are the actual physical particles you end up with? And very conveniently, the question has stipulated a choice of expanding. And you can choose any alpha naught, like you can just pick one minimum to expand around. And I'm going to choose alpha naught equals 0 for simplicity. So this prefactor just becomes 1 over root 2. And I'll also note that the way this is written now, when you work this, if you work this out for yourself with a little bit more time, I don't want you to get tripped up by factors of 2. So the v squared, so now, crucially, based on this problem stipulation, in fact, now the modulus, the modulus of phi naught squared now is actually 1/2 v squared. So note this factor of 2 in the way things are defined in this section of, in this part of the problem. All right, so now we have this, and I've rewritten the Lagrangian here that we need to expand, given our, and so we know what v is, we know how to expand. We know how to expand phi. We know what v is, and we have our Lagrangian. So it should be pretty simple to just plug these things in and see what we get. So in the first case, we expand the kinetic term. And so the kinetic term, the partial derivatives kill v, but the partial derivatives do act on h and chi. And so we end up with a kinetic term for h and a separate kinetic term for chi, which is nice. So it seems like we actually have now 2 scalar fields, which isn't uncommon. When you have like one complex scalar field, you can usually rewrite it as 2 real fields. And then let's look at the Yukawa term. The Yukawa term has 2 pieces. The scalar field acting on psi bar right, psi left, and its Hermitian conjugate. And then you can write this out by expanding like v plus h plus I chi. And so what we're going to get in the end is when we add the Hermitian conjugate, we get something real. And so if we group these terms together, we get v plus h times psi bar right, psi left plus psi bar left, psi right. And then we can do, unfortunately, I don't have time to actually do all the algebra, but we do a bit of algebra and we end up with this expression that's psi bar psi. And so we get a mass term for psi bar psi. And then the next part is the scalar potential. So this is like a bunch of algebra, but you basically just find psi star psi and then psi star psi squared. And then you do the same thing you did before, except slightly more complicated. You multiply out the potential, you do some algebra on the prefactors, and you find, one notable thing you find is that the prefactor in front of chi squared vanishes. So we find that chi squared is massless, and we expected to find a massless particle. And so in the end, we have this Lagrangian here, and the 3 particles are the h, the chi, and the psi. And the h is a scalar field, real scalar field, and it has a mass. -2 mu squared. The mass squared is -2 mu squared, where this is a positive number. And then we find another scalar field, chi, which is massless. And so this is the expected massless Goldstone boson. And then again, very nicely, we've now managed to create a mass term for the fermion. So we have a massive Dirac fermion, where the mass term is given by this. And I think that brings us to our time. But if there's time, I'm happy to answer questions. And if not, I'm happy to let you go.
Actually, we are running out of the time. You have been perfectly on time to finish the class. There are a couple of questions, but we have to go to the virtual visit. So if you do agree, I can write down on Zoom your email address in case students can send you the emails that are left unanswered. And if you send me the page of the problems, I can upload it.
Yeah, I'm happy to do that. Yeah, so, and yes, please feel free to email me questions and I can field them throughout the day.
Thanks a lot, Rachel. That is very, very clear. Also, the notes are very clear as you solve the problems and so on. So that's been very, very great. So let me tell to everybody the link to connect to the virtual visit. And I will write you also in this chat the email address of Rachel. So if you need, you can write directly an email to her. Rachel, let me, here there are the new address, copy address. Oh no. So maybe Rachel, you can write it directly. In the meantime, I can put it out to the other.
Let me stop sharing my screen.
Okay, I don't know why I cannot send to everybody the email.
Yes, I think I can only send you the email, but I'm sending it. I'm gonna put it in the chat, but I think it'll just go to you.
Yeah.
I can't. It looks like I can't send it to everybody. Oh no, maybe I can send it to everybody. Let me try that again because I think I'm the host actually.
I thought you should be able to do that. Yes.
Okay. Can everyone see it?
Yeah. I think yes, everybody can see.
Oh, and then let me also post the Zoom link then that you just sent me, Luca.
That'd be great. Thanks a lot.
Yeah. Okay.
You just sent it only to me in this case.
Yeah. Okay.
If anybody needs the link you can see from the chat, you can go directly to the Invisible web page, to the school web page. I'm sorry. In Indico, and there is the link to access to the virtual visit to the CERN that is running in a few minutes. And here you have the email address of Rachel, so you can find it and write to her in any case. And let's see, next Tuesday, Monday, there will not be classes, but it will be from Tuesday morning at 10 a.m. Central European time. Thanks a lot again, Rachel. It's been great. And have a nice weekend to everybody.